for number 1, we're writing up the ionization equation. So we've got HCN, our hydrocyanic acid, and our water. They're going to ionize. A hydrogen will be exchanged from our molecular acid to water. This is our acid, because it donates the hydrogen. This is our base, because it receives the hydrogen. In the reverse direction, cyanide receives a hydrogen to revert back to its molecular state, so that makes it a conjugate base. And water donates the hydrogen in the reverse reaction to revert back into water. That makes it a conjugate acid. So in the reverse direction, it donates. All right, for number 2, we just had to write out our equilibrium expression. Now for number 3, we got to do a whole bunch of math here. So, well, let's do some math. So for number 3, let's set up our ice table. So we've got HCN. Water is a pure substance, so recall that water's concentration cannot vary. But we do know the initial concentration here to be 0.25. We know the initial concentration of this to be 0. And recall the self-ionization of water, this is always present in the background, but we're going to make an assumption. The initial concentration of hydronium is equal to 0, even though it should be equal to 1 times 10 to the minus 7. It'll make for some simpler math, and in the end, as we'll kind of see when I jig through a few things, it doesn't make a big difference. Now these will each increase by a factor x. This will decrease by a factor x. So we end up with 0.25 minus x. We get x, and we get x. More on this later. So if Ka is equal to the concentration of cyanide, the concentration of hydronium, all over molecular hydrocyanic acid, we have our value of Ka given in the question. It's 6.2 times 10 to the negative 10. That'll be molarity. Our concentration of cyanide is x. Our concentration of hydronium will be x, and our concentration of HCN will be 2.25 subtract x. Remember this later. If we simplify, 6.2 times 0.25 subtract x. We can change this around to read 0 equals x squared plus 6.2 times 10 to the minus 10x subtract 1.55 times 10 to the negative 10. Now if we punch this into our quadratic function, we would see that negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is equal to 1, b is equal to 6.2 times 10 to the minus 10, and c is equal to negative 1.55 times 10 to the minus 10. Right, so now that we've solved for x, we know x to be 1.24 times 10 to the minus 5 molarity. That's the concentration of the hydronium ion. We can now solve for the pH. Our answer is a pH of 4.9. Now, question number 5 has us make an interesting assumption. Well, if we go back to our assumption that the equilibrium concentration of HCN is equal to 0.25 subtract x, that's 0.25 subtract 1.24 times 10 to the negative 5, we get, rounded 0.25. So in weak acids, X is so small that we can make another assumption here. And this assumption is that your 0.25 minus X in this scenario is roughly equal to 0.25. Our X is going to have an insignificant impact on the change in concentration of our molecular acid. Now, if we were to, using assumption number 2, if we substitute 0.25 for 0.25 minus x, 0.25 times that, we get 1.55 times 10 to the minus 10 equals x squared. X equals 1.24 times 10 to the minus 5. Now, wasn't that a ton easier than using the quadratic equation? All right. So if you make these two assumptions, it won't impact your final answer, and it'll make your math a whole lot more simple. All right. You're welcome. Have fun, everybody.